All right, continuing with our discussion of reactions in aqueous solutions. Here's part 2 of our video notes. In this section, we're going to talk mostly about oxidation-reduction reactions and how to balance those, as well as some concentration chemistry, so how to do molarity and dilutions and titrations. So moving on to oxidation and reduction reactions. So an oxidation occurs when an atom or an ion loses electrons, and reduction occurs when an atom or an ion gains electrons. So kind of two ways to remember this. Leo says GER, which just means lose electrons, you're oxidated, gain electrons, reduction. Or I always learned growing up oil rig, oxidation involves loss of electrons and reduction involves gain. Whatever one you remember to help you keep it straight. And they always occur together. One can't happen without the other one. So determine if an oxidation-reduction reaction has occurred, we've got to look at the oxidation numbers to see if they change. And so here's how to do that. Basically, when you're signing oxidation numbers, elements in their elemental form, so if it's just like magnesium or bromide, remember it's a diatomic molecule, they have an oxidation number of 0. If it's a monatomic ion, whatever its charge is also its oxidation number. So if you just had like sodium plus, it would be a +1. Nonmetals tend to have a negative oxidation number, although some are positive in certain compounds or ions. So oxygen is pretty much always going to be -2, just like you'd expect it to be given its group. But when it's in a peroxide ion, it has an oxidation number of -1. So that's kind of like an exception. One thing to be careful of, though, hydrogen peroxide is not an ion. H2O2, hydrogen peroxide, is not an ion. So in this case, O still has oxidation of -2, even though it's called hydrogen peroxide. Just don't get that confused. Hydrogen is going to be -1 when bonded to a metal, or +1 when bonded to a nonmetal. Fluorine is always going to be -1, and the other halogens are pretty much going to be -1 as well. There's some exceptions, but like the oxyan ions, like we talked about last set of notes. But really, you can pretty much count on them being -1. The sum of the oxidation numbers in a neutral compound is going to be 0, so you can use that to help you figure out oxidation numbers. And then if it's a polyatomic ion, the charge of that ion is also going to be the sum of the oxidation numbers. So just put it all together for you in one slide, so you have that for your reference. So oxidation-reduction, a species is oxidized when it loses electrons. So again, we're assigning our oxidation numbers. Zinc is just an element, so it's got a 0. Hydrogen plus, so its oxidation number is +1. Zinc 2+, it's an ion, so its oxidation number is +2. And H2 is just elemental hydrogen, so it's 0. So zinc goes from a 0 over here to a 2+ over here. So here zinc loses 2 electrons to go from neutral zinc metal to the 2+ ions. So it was oxidized. Right? It lost electrons, lost its negative charge, and became more positive. Then conversely, something is reduced when it gains electrons, just like I said before. So each of the H pluses gain an electron, combined to form H2, so they've been reduced. What is reduced is called the oxidizing agent. So basically, it gets a little flip-flop. This can get confusing sometimes. So hydrogen oxidizes zinc by taking electrons from it. So it's the oxidizing agent. And then zinc reduces hydrogen by giving it electrons. It's the reducing agent. So zinc is oxidized, and it's the reducing agent. Common reactions that are oxidation reduction are these displacement reactions. So an ion oxidizes an element, and the ions get reduced. So here, if we've got hydrochloric acid, H plus Cl, strong acid, so it completely dissociates. In magnesium metal, magnesium down here, we've got our oxidation numbers is 0. HCl is -1, +1. Those are their oxidation numbers. We put them together, and now H2 is being formed, and it's got a 0. In magnesium chloride, magnesium is now +2. So you can see you got that going on. The magnesium was reduced. Another example, copper plus silver ions. produce copper 2 plus silver solid. So kind of the same idea going on, but just got to remember that it's not necessarily, or it's not reversible, so it doesn't work the other way around. You don't put copper ions plus silver together to create these guys, to create solid copper. It doesn't work that way. It only works one way. Something that could be handy for you guys is this thing called the activity series. So it's a list of metals in order of decreasing ease of oxidation. So metals can be oxidized by the metals below it, but not so much by the metals above it. And then only metals above H plus hydrogen will react with acids to form H2. That's why hydrogen there is sort of blue for you, just to point it out. So they can be oxidized by things below it. Then again, here's just one for your notes, or the whole larger version. So how to balance oxidation-reduction equations. So pretty much everybody does this by what's called the half reaction method. You're only responsible for balancing oxidation-reduction reactions in acidic solutions. Your textbook will talk about basic solutions, but we can pretty much ignore that. We don't have to worry about that because the AP board doesn't care about that anymore. So we're going to be looking at balancing oxidation-reduction reactions in acidic solutions. Again, half reaction method. So how do you do this? Basically, you treat the reactions, at least on paper, you sort of break them up into two separate ones, figure out what's going on, balance them up, and then put them back together at the end. So what you do, you assign your oxidation numbers to figure out who's being oxidized and what's being reduced, and then write out the oxidation reduction half reactions. Balance each of the half reactions. So this is where it gets a little bit different from just balancing regular reactions. You're going to balance anything other than hydrogen and oxygen first, just in the standard way that you would always do it. You're going to balance oxygens by adding H2O to the opposite side, and then you're going to balance out the hydrogens that you probably added by adding H+. And then you're going to balance all your charges by adding electrons. And then multiply the half reactions so that all your electrons are the same, and then add them together and cancel stuff out and make sure everything is all balanced. So let's look at an example of this. So consider the reaction between the permanganate ion and oxalate ion. This is something we're going to do in class. So you got your manganate and your oxalate, and this is you're going to get manganese, 2+ and carbon dioxide. So first thing we do is assign our oxidation numbers. Oxygen is always going to be a -2. We've got 4 of them, so that means it's like a total of -8. And since the whole ion has a -1 charge, that means the manganese must be +7. So manganese is +7, the carbon is +3. We're looking over here, manganese is +2, and carbon is +4. So the manganese is going from +7 to +2, so it's being reduced. And the carbon goes from +3 to +4, so it's being oxidized. So first, we'll look at the oxidation half reaction. Got your oxalate ion going to carbon dioxide. And so we're going to start off, we're just going to balance our carbon, just like we always would. So that's balanced up, great. Oxygen is now balanced. We've got 4 oxygens and 4 oxygens, so we don't have to do anything there. But our electrons are not. If you recall back to our oxidation numbers, we know that there was 2 electrons moved around. And so we're gonna add our 2 electrons to our products. On the other side, the reduction reaction, the manganese is already all balanced, but we don't have any oxygen over here. So we're going to add 4 waters to the right side. So now our oxygens are all balanced up, but now we've got hydrogen, so we got to add some hydrogen ions, 8 hydrogen ions to the left side. So now all of our elements are all balanced up. Great. What about charges? Remember, it went from a +7 to a +2, so we're going to add 5 electrons to the left side over there. So we're looking like that. Now we're going to combine everything together, or at least we're going to look at them together. We're not combining them yet. So this guy, the problem is this guy added 2 electrons. We've got 5 electrons over here. So we have to balance our electrons. So basically we're going to multiply the first reaction by 5 and the second reaction by 2. And so this is what we end up getting. Now we can add everything all together. So everything's all together, and we cancel out whatever is in common. The only thing that appears on both sides are the electrons, so we can just drop them out. They cancel each other. And here's our final balanced equation. So you might see something like this on the AP exam, and it might be just a simple question. Might just say, what are the lowest the coefficients in this reaction, and it might seem really easy to you at first, but when you see these, you want to double check your oxidation numbers to make sure that you don't have some kind of oxidation reduction going on to make your life a little bit more complicated, basically. All right, moving on to the last bit of this section, we're going to talk about concentrations of these aqueous solutions, and we talk about concentrations in terms of molarity. So two solutions could contain the same compounds, so you could have different, but just different amounts. So you could have salt water, right, but different levels of salt water. And molarity is what we use to measure this. So the molarity is just defined by the moles of a solute over the volume of the solution in liters. So make sure you're always doing this in liters. So that'll be kind of like a little mini conversion you're probably going to have to do for many of the practice problems. If you want to create a solution from a solid, create a solution of a known molarity, you weigh out some mass, whatever you need, depending on what kind of molarity you're working on, because when you know the mass, you know the moles of the solute. And you put that solute in a volumetric flask. This is a volumetric flask over here. The volumetric flasks are marked to only measure one volume only. So you'll see we've got like 250 mil, 500 mils, 1 liter mil. They don't have a lot of lines. They have one line, and they're the most accurate way to measure a liquid. All right, you don't do this. You could do this you could do this kind of thing with a graduated cylinder, and yeah, that would be accurate. That's more accurate than a beaker, but it's not as accurate as a volumetric flask. So that's the most accurate way of doing measuring these. Then we have a graduated cylinder, and then when the lines on beakers are really more for estimation, they could be off by quite a bit, honestly. So those are basically worthless for measuring fluids where you want like precise amounts. So a volumetric flask, you add it to the volumetric flask, and then you add your solvent, which is probably water, and you fill it up till it gets to the line, wherever that line is, and you have exactly 500 mils or whatever volume of solution you're going for. Dilutions, very similar. You can dilute a concentrated solution. So you take a pipette. Again, they make volumetric pipettes, so you know that you've got exactly 25 mils or 10 mils or 2 mils or 1 mil or whatever. So you can pull out a precise amount, accurate and precise amount from this solution, put it into a new flask, and then add solvent to the neck of the new flasks. One thing definitely always remember when you're doing this, you probably heard this expression, do what you oughta, add acid or base to water. You don't want to add your water to your acid because it's an exothermic reaction. It could actually splatter, and that could be bad because obviously we don't want splattering acid. That always ends up in somebody's eyes, right? That's what you always learned. So that's how to make a dilution. Again, you want to be sure that you're using volumetric flasks or volumetric pipettes for this. You can figure out the new molarity of the solution using this handy equation. The M and C are the concentrated and the dilute solutions, so the molarity of the first one and the volume of the first one, and the molarity of the second and the volume of the second. So sometimes you hear people say C1, V1, C2, V2, C for concentration, whatever. It's all just a proportion. You can use that to figure out what your new molarity is. And then where would this come into play in your calculations? Well, you can do a lot of different things with these molarities. So like if you have the gram of a substance, then you use the molar mass. You can figure out how many moles you have, and then you could figure out using your coefficients, your balance coefficients, the moles of substance B, and then you could use the volume to figure out the molarity of that, or you could use the molarity of a solution to figure out how much solution would be made containing that substance. So kind of familiar thing going from grams to moles, and once you're in moles, things are a little bit more easy to work with. And titrations. So something you can use, a titration as a technique used to figure out the concentration of solute, an unknown concentration of a solute in a solution, and we'll definitely be doing this. And basically what you do is you've got your acid, for example this one, you've got your acid added to this flask and some kind of indicator, and then you titrate in some base. So you're adding in base dropwise, and then as soon as this changes color, this indicator, that tells you, it really indicates a pH, assuming you've chosen a indicator that it's going to change at about pH 7. So you would know that, okay, now you've got equal amounts, and since you know the concentration of this solution, now you know if you added so many mils of this, you can figure out how many moles of that you added, and since you're at the equivalence point, you have the same number of moles of the acid, basically how that works. So kind of shown down here, you've got your volume of your standard solution. So you use the molarity to figure out the moles in your standard solution, and then using your balance coefficients, because you know what reaction's going on, now you know the moles of solute in your unknown solution, and then you know how much volume you use, so now you can figure out the concentration of that solution. So we see this in redox. We use titrations in redox, and probably some acid-base titrations as well. And that is that.